Transition metals now, quite a large A-level A2 topic. The first thing to be aware of is that the transition metals are found in what's known as the D block of the periodic table. Here's your S block, your P block, your D block. Now, in order for a metal to be classified as a transition metal, they must form at least one stable ion with a part-full D shell of electrons. So you can see that's literally what the definition is here, an element that forms at least one stable ion with a partially filled D orbital. And therefore, scandium here and zinc over here are not classified as transition metals. The reason for that is because scandium only forms 3+ ions, which have an empty 3d orbital, so they're not fulfilling this need for a partially filled d orbital, and zinc only forms Zn2+ ions, which have a full 3d orbital, so again, that's not partially filled. The properties of transition metals you've probably come across before. They have variable oxidation states. You might have seen, for example, Fe2+, Fe3+, exists as ions with more than one oxidation state. This actually enables them to take place in many redox reactions. The ions of transition metal elements form coloured compounds. Copper 2+ is blue, Fe2+ is green. Transition metals can be super useful because often they can act as catalysts, and the reason for that is the range of oxidation states that they exhibit allow the transition metals to catalyse other reactions, such as ion, which is the catalyst in the Haber process used to make ammonium, vanadium 5 oxide, which is the catalyst used in the contact process used to make sulfuric acid. Another property of transition metals is they form complex ions. They form when a ligand forms coordinate bonds with a transition metal ion. So we've introduced some new terms here. First of all, a complex ion is a central metal atom or ion which is surrounded by ligands. Key is our definition of a ligand. It is an ion or molecule with a lone pair of electrons that forms a coordinate bond with a transition metal. Remember, a coordinate bond is when both electrons are donated by the same atom. So these two super crucial definitions, again, the complex ion, a central metal atom or ion surrounded by ligands. The ligands are an ion or molecule with a lone pair of electrons that forms a coordinate bond with a transition metal. Let's now look at the different types of ligand. So the first one we're going to look at is the monodentate ligand. So we've taken our definition of a ligand. The key thing about a monodentate ligand is that a single coordinate bond is formed with a transition metal ion. So let's look at some examples. So you'll be familiar with water and ammonia. Water's oxygen has 2 lone pairs of electrons. The nitrogen and ammonia has 1 lone pair. Now water and ammonia are both neutral monodentate ligands, and they're a similar size to each other. Now we have a chloride ion and a cyanide ion. These are both negatively charged monodentate ligands, and they're both larger than water and ammonia. So our complex ions, which we know consist of a central metal atom or ion surrounded by ligands. Now there's a very specific convention when it comes to writing them. So we'll take our first example here. So the first thing to be aware of is that you have square brackets around the entire complex. Then you have round brackets around your ligand. That's only if the ligand is a molecule. In our second example here, again, we can see our square brackets. This 2 minus here and the 2 plus here represents the overall charge of the complex. And then the 4 here represents the number of each type of ligand surrounding the central metal ion. In the case of water, it was 6. Now the coordination number is the number of coordinate bonds formed to a central metal ion. And we're going to tie in the coordination number together with the oxidation states. So to find the oxidation state of the transition metal ion, we're going to do the overall charge of the complex minus the combined charge of the ligands. Let's look at an example. So the overall charge of the complex is 2+. Then we need to minus the combined charge of the ligands. This water ligand is neutral, so it's 6 times 0, which is 0, to get a final answer of +2. And so we can infer that the oxidation state of the transition metal ion, in this case the cobalt, must be CO2+. And remember, we use Roman numerals to represent that. Let's take another example now. So the overall charge on the complex is -1. Then we need to subtract the combined charge of the ligands. We have a chloride ion here, which remember is -1. There's 4 of them, so it's -4. So that gives us Fe3+, ion 3. Now, as we've already seen, ammonia and water are similar size and they're both uncharged, and this means that ligand exchange can occur between the ammonia and the water without a change in coordination number, such as the case here, where you have in the original complex ion water reacting with ammonia, and as you can see here, in effect they've swapped places. You'll find that incomplete substitution can also occur with copper 2. So rather than a straight swap between the ammonia and the water here, we've got 4 of the water ligands swapping out for ammonia, as we see here. And in both of these examples, the coordination numbers we can see remain 6. But if a larger charged ligand, such as the chloride ion, substitutes a smaller uncharged ligand, such as ammonia or water, it can cause a change in coordination number. So if we go from our small neutral water ligand we replaced with the chloride, we see a change in coordination number to 4. Whereas before with the monodentate ligands, we saw that they were molecules or ions with a lone pair of electrons that form a single coordinate bond with the transition metal ion. What about if you have bidentate or multidentate ligands? This time, these are molecules or ions with lone pairs of electrons that form 2 coordinate bonds with a transition metal ion. So good examples of bidentate ligands include ethane 1,2-diamine and ethane diorate. The multidentate ligands, exactly the same definition, but this time we have more than 2 coordinate bonds formed with a transition metal. This is an incredibly complex molecule, the EDTA4-. Be aware, in your exam you don't need to be able to draw it, thank goodness, but you do need to know that it can form 6 dative bonds and that it has a charge of -4. Now you'll be familiar with hemoglobin. It's a pigment found in our red blood cells. It actually contains heme, which refers to the fact that it contains an iron 2 complex with a multidentate ligand. Here, oxygen forms a coordinate bond to the iron 2 in heme, enabling the oxygen to be transported in our blood, which is used in respiration. The Fe2+ to O2 bond is weak, as oxygen is not a very good ligand, and this means that the oxygen molecule can be taken up easily by cells where it's needed in respiration. Ligands that form stronger bonds than oxygen bond irreversibly to iron 2, and this is actually the chemistry which explains why carbon monoxide here is so toxic. Because carbon monoxide is a ligand which forms a stronger bond to the iron, it binds preferentially to the iron 2 displacing the oxygen, meaning that a person effectively suffocates if they're exposed to too much carbon monoxide. Complex ions containing bidentate or multidentate ligands are called chelates. The substitution of monodentate ligands with a bidentate or multidentate ligand leads to a more stable complex, and this is known as the chelate effect. Now, the chelate effect occurs because the entropy, so the amount of disorder in the reaction, increases. As you can see, there are 2 moles on the left, 7 moles on the right. You can add that up. 2 moles versus 7. Now, our enthalpy change is usually small, as the number and type of bonds are similar in both complexes, so a positive entropy change is likely to lead to a negative Gibbs free energy, meaning that the reaction is spontaneous, it's feasible, and therefore the products are stable. Chelates can be used to effectively remove D-block metal ions from solution, so we can use EDTA to remove poisonous heavy metal ions from rivers. This occurs because the EDTA substitutes out the water due to the chelate effect. EDTA complexes are not toxic, so this is a very useful way in order to remove any poisons from river water. The concentration of copper 2 ions in a sample of water was determined to be this. This result was checked by titrating a sample of the water with a solution containing EDTA4- ions with a concentration of this. Calculate the volume of EDTA4- solution needed to react with 30 centimeters cubed sample of the water. The first thing we're going to do is find the amount of copper 2 ions present in the sample. We'll use the balanced symbol equation to calculate the number of moles of EDTA4- required to react fully with the copper 2 ions, and that will enable us to calculate the volume of EDTA needed. So we'll start by finding the number of moles of Cu2+ ions in the sample. So just pulling these numbers from the question, just make sure that 30 centimeters cubed is converted to decimeters cubed to get a number of moles of 1.94 times 10 to the minus 6. We're now going to use stoichiometry to determine the moles of EDTA4- needed to react fully with the copper 2 ions. So we can see they react in a 1-to-1 ratio, so we can therefore infer that the number remains the same. And then lastly, let's find the volume of EDTA4- needed. And then the last step to convert that into centimeters cubed is multiplying by 1,000. Now we need to move on to the shapes of complex ions. It will remind you a lot of the V-separ theory we did earlier on in the course, so do bear everything you learnt there in mind here. The first thing you need to be aware of is that transition metal ions commonly form octahedral complexes with small ligands such as water and ammonia. So you can see the coordination number here is 6. We have the octahedral shape. Do make sure you draw square brackets and include the charge if a charge is present. With larger ligands, you commonly get a tetrahedral complex with the transition metal ion present in the middle. You have your 4 ligands around the edge. This time you've got your chloride ion, which is a larger ligand when compared with water and ammonia. You'd expect your typical tetrahedral bond angle of 109.5. Very occasionally you get a square planar complex with larger ligands as opposed to the tetrahedral, such is the case with this cyanide ion. And here the bond angle is 90 degrees. The simplest shape is obviously linear with a bond angle of 180 degrees. This forms when you have silver as your transition metal ion surrounded by 2 ammonia ligands. Now, this particular complex ion here is actually Tollin's reagent, which remember is used to distinguish between aldehydes and ketones. Aldehydes reduce this complex ion to silver, a silver mirror. It's possible to get geometric isomerism with octahedral complexes. So in essence, the complex ion is the same. You have a cobalt transition metal ion located in the middle of our complex ion. You're going to have 2 different ligands. One of them is ammonia, one of them is water. Now, the way in which these ligands can arrange themselves varies, hence the presence of geometrical isomerism. In this case, the water molecules are located opposite each other. Remember, we learned when we looked at isomerism, this indicates that these are trans isomers, or E. They are enemies, they are on opposite sides. In this case, the water molecules are next to each other. They are on the same side, so they are Z or cis isomers, whichever you prefer. One of the most interesting cases of geometrical isomerism is if we consider the drug cisplatin, which is a cancer drug. Now, cisplatin is made up of platinum surrounded by 2 ammonia ligands, 2 chloride ligands. Now, if those chloride ligands are on the same side, as is the case of the Z isomer or the cis isomer, this is an anti-cancer drug known as cisplatin. However, if the chloride ions are on opposite sides, they are E isomers or trans, you'll actually find that this will have no therapeutic effect on someone suffering from cancer. And just to reiterate, geometric isomerism in complex ions requires 2 different ligands to be present, as we've seen in the last 2 examples here. Then it gets even more complicated. We're now looking at optical isomerism in octahedral complexes. Just to remind you, optical isomers are non-superimposable mirror images and are said to be chiral. Now, in order for optical isomerism to occur in complex ions, you require 2 or more bidentate ligands in an octahedral complex. Remember that bidentate ligands are molecules or ions with lone pairs of electrons that form 2 coordinate bonds with the transition metal ion. So here and here, here and here, here and here. This is obviously a super complex bidentate ligand. So actually we can use the 2 letters En to represent this entire bidentate ligand. And in the exam, it's perfectly okay to substitute this for En, as we can see here. Now the dotted line is supposed to represent, in effect, our mirror, so you can see that these are both mirror images of each other. They are non-superimposable mirror images. Now we've already pointed out that transition metals have formed coloured compounds, but now we really need to understand why. And it's all due to the splitting of the d orbitals into different energy levels. Because if you remember, what I taught you is that transition metals by definition have incomplete d orbitals, which means there'll always be at least one unpaired electron in their d orbitals. So just to remind you of an earlier part of the specification, we have selenium here. It's not a transition metal. This is the electron configuration of selenium, showing the electrons present in the various orbitals. So obviously we're talking a lot with transition metal elements about d orbitals. So I want you to see here, look, one of the reasons why selenium isn't a transition metal is because every single orbital is fully paired. Now the first thing to be aware of is that 3D sublevel. We know it consists of 5 orbitals, but the truth of the matter is that in the case of transition metal ions, when ligands form coordinate bonds with them, the metal d orbitals split into 2 energy levels, as we see here, as opposed to the more typical representation there. And because transition metals by definition have incomplete d orbitals, this means that there'll always be at least one unpaired electron in their d orbitals. So as a coordinate bond forms between the ligand and the transition metal ion, an electron is excited from the lower energy level, which we call the ground state, to a higher energy level, and that occurs due to certain frequencies of visible light being absorbed. But at the same time, remember, visible light is a spectrum. It contains lots of different colours. Any frequencies of visible light which aren't absorbed, they're transmitted. That's a chemistry term. In physics, you might have used the word reflected. These are the frequencies that correspond to a particular colour we see. So if a particular solution absorbs red but transmits green, the solution will appear green. Scandium and zinc we've met before, they're not transition metals, in part because they do not have a partially filled d orbital, so electrons therefore can't be promoted from a lower energy level to a higher energy level, and they can't transmit any colours. Now, there are certain equations that link the colour, wavelength and frequency of the light absorbed with the energy difference between the split d orbitals, and they are this first equation, which states the energy difference between split orbitals given in joules equals Planck's constant, which has a particular value, multiplied by the frequency of light, and that delta E again equals Planck's constant multiplied by the speed of light divided by the wavelength of light absorbed. And now going into greater detail about the colour of light you'd expect to see. The EM spectrum, remember, shows that the visible light consists of the following colours. Now red has the longest wavelength and therefore the lowest frequency, and it is lowest in energy. Violet at this end has the shortest wavelength, it's highest in frequency and highest in energy. And so the colour of a transition metal ion depends on the energy gap between the split d orbitals, delta E. The colour of the transition metal complex can be altered by changing the ligand, so swapping out ammonia for water, changing the coordination number and changing the oxidation state. Let's practice using the Planck constant now. I'm just writing down the equation there. Remember, this is the energy difference between split orbitals. This is Planck's constant. This is the frequency of light absorbed. When a d electron moves from the ground state to the excited state in a copper complex, the energy change is this. Here's Planck's constant. Calculate the frequency of the light absorbed. There's the final answer. A solution containing complex Fe3+ ions is placed in a colorimeter and found to absorb light of wavelength 490 nanometers. Here's your speed of light. Here's Planck's constant. Calculate the energy in joules gained by each excited electron in the absorption at 490 nanometers. Here's our equation. This is your wavelength of light absorbed. This is Planck's constant. This is the speed of light. Just make sure that gets converted into the equivalent in meters. So that's 4.90 times 10 to the minus 7. Our final answer is 4.06 times 10 to the minus 19 joules. Variable oxidation states. As we've already mentioned, transition metals show variable oxidation states. For example, iron 2, iron 3, copper 1, copper 2, copper 3. The thing to be aware of here is that the transition metal compounds with high oxidation states usually act as oxidizing agents, and that makes sense really, because remember, oxidizing agents are by definition reduced, so that high oxidation state that they start with easily allows them to become reduced. A good example here is manganese 7 in MnO4-. We can work out the oxidation state. Oxygen is -2, which means that the manganese must be +7 to give the overall oxidation number of -1. Compounds with a low oxidation state are usually reducing agents. These are by definition oxidized. So again, that makes sense that they start at a low oxidation state. Here, iron 2 is starting at +2. The redox potential for a transition metal ion changing from a higher to a lower oxidation state is influenced by both pH and the ligand present. So we've got the oxidation states of D block ions moving from titanium to vanadium, chromium, manganese, iron, cobalt, nickel and copper. So as we can see, a huge variety in their oxidation states. The blue boxes indicate the most common oxidation states for each element. So titanium most often exists as titanium 4, vanadium exists as vanadium 4 and 5. Unfortunately, there's an awful lot of learning off by heart in this part of the specification, so I've listed the various transition elements as well as their species and the colour each of these species is. Remember, this is taken from my SwH Learning revision guide. So if we look at vanadium 5, this species is VO2+. You can check. Look, that will be -2. There's 2 of them, it's -4. The overall oxidation state is +1, so that's why that is +5. So you could do that for each of these species, practicing your oxidation states. Now the vanadium 4 exists as the VO2+ species. This is blue. V3+ is green. Vanadium 1 V2+ is violet. One thing to be aware of is that zinc in acidic conditions is a strong reducing agent, and that when zinc is added to vanadium 5 in acidic conditions, the colour change will go from yellow to blue to green to violet. So tracking down these various colours here, and that's because the vanadium is being reduced from vanadium 5 all the way down to vanadium 1. Iron 2 is more straightforward. Here's your complex ion. Iron 2 is green. You'll have met this when you were learning your various anion and cation tests. Remember, when you add sodium hydroxide to iron 2, you get a green precipitate. The same reaction this time with iron 3, you get a brown precipitate. What about chromium? Well, Cr2 is blue, Cr3 is red-yellow. Manganese now, manganese 7, MnO4- is purple, Mn2+ is pale pink, and then lastly cobalt 2 is brown, cobalt 3 is yellow. Like I said, you will need to learn these colours off by heart. I've already mentioned that Tollin's reagent is a complex ion which is used to distinguish between aldehydes and ketones. Remember that aldehydes reduce the silver in Tollin's reagent to solid silver, and here's an equation representing that reduction reaction, the addition of electrons in order to produce that solid silver. Because it's a redox reaction, you'll also get the oxidation reaction occurring with your aldehyde here. This is ethanol being oxidized to ethanoic acid. You could be asked to answer a redox titration calculations involving transition metals. This is a good example here. A 50 centimeters cubed sample of solution containing this complex ion was added to 50 centimeters cubed of dilute sulfuric acid. It was made up to 250 centimeters cubed of solution in a volumetric flask. 25 centimeter cubed sample of this solution was titrated with this concentration of KMnO4. At the end point of the reaction, when the solution changes colour from pale green to pink, the volume of KMnO4 added was 16.50 centimeters cubed. We're being asked to calculate the concentration of iron 2 ions in the original solution, and here's our equation. So it does seem quite complicated. What we are going to start by doing is calculating the number of moles of KMnO4 that react. That will be quite straightforward, remember, because we're going to use this equation which states that concentration times volume equals the number of moles. Then we can use the stoichiometry in the equation to work out the number of moles of Fe2 plus ions present in the 25 centimetre cubed sample. And then we'll multiply that number by 10 in order to gain an idea of the number of moles of Fe2 plus in the original solution. And then we can finally sub our numbers back into here in order to find the original ion 2 concentration. But beginning at the beginning with the number of moles of KMnO4, just underlining the key numbers here, just dividing by 1,000 to get that into decimeters cubed. So we have 4.95 times 10 to the minus 4 moles of KMnO4. Now we're using the stoichiometry to work out the number of moles of Fe2 plus in the 25 centimetre cubed sample. So it's 1 to 5, so we need to multiply that number that we just calculated by 5. And then multiply it by 10 so that we know the number of moles present in 250 centimetres cubed of solution. And then our final step to find the concentration is to take that number of moles we just calculated and then divide by the volume given in the question as being the volume of the original sample, 50 centimetres cubed. So our final answer here is 0.496 as our concentration. Let's take another calculation now. So a 1.265 gram sample of this impure compound, which was dissolved in an excess of dilute sulfuric acid and made up to 250 centimetres cubed of solution, 50 centimetres cubed of this solution, decolorized 39.35 centimetres cubed of this concentration of potassium manganate 7. Calculate the percentage by mass in the original sample. Now this is the equation for the overall reaction. So our first step will be to find the number of moles of MnO4 minus that react. We'll then use the stoichiometry here to work out the number of moles of FeC2O4 present in the 50 centimetre cubed sample of the solution. We'll then multiply it up to find out the number of moles in 250 centimetres cubed of the original solution. And then we can just do some simple maths to find the mass of FeC2O4, and then we can use that to find the percentage by mass. So the number of moles of MnO4 minus, first of all. Now let's use the stoichiometry to find the number of moles of FeC2O4. So there's a 3 here, a 5 here, so we need to do 5/3 multiplied by the number of moles of the MnO4 minus. And then in a similar way to the question before, we need to multiply that up to find the number of moles present in the original solution, so we need to multiply it by 5. So close. So now let's find the mass. So we're doing MR times number of moles. You need to use your periodic table to find the MR of this. It will come out as being 179.8. And then finally, to find the percentage of the hydrated FeC2O4, we're going to do the mass we just calculated over the original mass, 1.265 times by 100 to get a final answer of 85.8%. An awful lot of learning things off by heart in this part of the specification. So the use now of transition metals as catalysts, that'll have come up frequently the whole time you've studied chemistry, right from when you were young. So remember that a catalyst, by definition, increases the rate of a chemical reaction usefully without being used up. How do they do this? By providing an alternative reaction pathway with lower activation energy. Remember, activation energy is the minimum amount of energy required for a reaction to take place. Now, there are two types of catalysts. The first one is heterogeneous. The second one is homogeneous. So a heterogeneous catalyst is one that is in a different phase from the reactant. So really that means a different state. They are usually solid, with your reactants being in either aqueous or gaseous state. The reaction occurs at active sites on the surface of the catalyst. Whereas a homogeneous catalyst, this is a catalyst that is in the same phase as the reactants, and the reaction proceeds through an intermediate species. The reason why transition metals can be used as catalysts is because, as we keep saying, they have variable oxidation states. The partially filled d orbitals can be used to form weak bonds with the reactants. This weakens the bonds within the reactants and holds the reactants close together in the correct orientation for the reaction. So looking in more detail how solid heterogeneous catalysts work, the reactants adsorb onto the active sites on the surface of the catalyst. This weakens the bonds in the reactants, lowering the activation energy, enabling the reaction to take place. The products desorb. This means that they leave the surface of the catalyst, and as you'd expect, the catalyst is left unchanged. What factors affect a heterogeneous catalyst? Well, first of all, the strength of that adsorption. If the absorption to the metal is too strong, the products cannot be released. If the adsorption to the metal is too weak, the reactants are not brought together and the bonds are not weakened. Surface area is the second factor affecting heterogeneous catalysts. Increasing the surface area increases the effectiveness of a solid catalyst, and a support medium is often used in order to maximize the surface area and to minimize the cost. Now, poisoning may occur. This is when impurities in the mixture can poison the catalyst, blocking the active sites, reducing its efficiency, meaning that catalysts must be replaced, which can be very expensive. Let's look at a couple of examples of heterogeneous catalysts. The one you'll be more familiar with probably is the iron used in the Haber process, a reversible reaction used to make ammonia. Now remember that iron catalyst increases the rate of both the forward and reverse reactions equally. The catalyst is made more efficient by using powdered iron or a support medium to increase the surface area. In terms of these poisons, it's actually going to be sulfur compounds here which can poison the iron catalyst. The sulfur compounds strongly adsorb onto the active sites, blocking them, preventing the reactants from absorbing. And we can reduce this by removing impurities from the reactants before they pass over the catalyst. A second example of a heterogeneous catalyst is the contact process used to make sulfuric acid. Vanadium 5 oxide this time is used as the catalyst due to its variable oxidation states, and it works in two states. We can see the vanadium moving through from being +5 here to +4 here. It's been reduced, and then in the second stage it goes from +4 to +5. It's been oxidized. So overall, it's unchanged, and each of these two steps has a lower activation energy than the uncatalyzed single step, so the reaction is sped up. What about the use of Fe2+, this time as a homogeneous catalyst, one which is in the same phase as the reactants? So Fe2+ can be used as a catalyst in the reaction between I- and S2O8- ions. I'll show you the overall equation here. Now, the iron ions act as a catalyst because they have variable oxidation states, and they are positive ions, so they attract the negative ions, and the catalyzed reaction occurs in the following step. So here's step 1. So as you can see, the Fe2+ remains unchanged, and what happens is the iron ions are providing an alternative reaction route with lower activation energy. Now, the Fe3+ ions we've also mentioned are as effective as the Fe2+ ions in catalyzing the reaction, and that's because both steps 1 and 2 can occur in any order. The uncatalyzed reaction is very slow because the negative ions repel each other, so the activation energy is high. Autocatalytic reactions. Now, autocatalysis is when one of the products of the reaction then acts as a catalyst for the reaction. So that really is a very ideal situation. If we see this graph here on the y-axis, we have the concentration of reactants. Then we have time on the x-axis. As you would expect, the reaction starts slowly because we haven't produced any product yet that can act as a catalyst. But then as more of that product forms, as more of that catalyst forms, the rate of reaction increases. We see a steeper gradient, and then eventually that rate decreases as the reactants are used up. Now, a good example of this is the reaction between oxalic acid and acidified potassium manganate 7. This is the overall equation here. Now, the Mn2 plus product is what's going to be acting as the catalyst. Because it's obviously not present in the reactants at the beginning, the rate is slow. And a large part of that is due to these two ions being negatively charged and therefore repelling, leading to the reaction having a high activation energy. However, as the Mn2 plus forms, it can now act as a catalyst in the following two steps. The Mn2 plus obviously needs to be regenerated, because after all, a catalyst isn't used up, and it is the Mn3 plus being reduced to the Mn2 plus by C2O42 minus that does that. And then the Mn2 plus is then oxidized back to Mn3 plus by MnO4 minus. We can track this reaction using a colorimeter, and that's because we learnt the various colors, didn't we? MnO4 minus is purple, whilst all the other reactants and products are colorless. When a transition metal salt is dissolved in water, what happens is the water molecules surround the transition metal. The transition metal ions are surrounded by water ligands, and we call these aqua ions. How does the coordinate bond or dative bond form? It's the oxygen atom of the water donating a pair of electrons to form a coordinate bond with, in this case, copper. We see several other examples here. Don't forget that you need square brackets with your charge to represent that it's a 2 plus ion. Count the number of water molecules around the outside. There's 6. This means that the aqua ions are octahedral shaped here. And we even say that aluminium can form aqua ions despite the fact that aluminium isn't a transition metal. One thing to be aware of is that aqua ions with an M3 plus metal ion at the centre are more acidic than those with an M2 plus ion. Obviously, M stands for the transition metal or aluminium, so therefore the pH of Fe3 plus is approximately 1.5, whereas Fe2 plus is almost neutral. So what is the reason for that? In this case, Fe3 plus ions are smaller, more highly charged than the Fe2 plus ions, and therefore the Fe3 plus ions are more strongly polarizing. They weaken the oxygen-hydrogen bonds in the water ligands more, and then the water ligands can then more easily release a H plus ion into the solution, and it's that H plus ion which makes it more acidic. So the reason here explains why our M3 plus ions produce solutions with lower pHs compared with M2 plus ions, and fundamentally that's due to more H plus ions being donated. Now, if a base is, which remember is a proton acceptor, is added to an aqua ion solution, it will remove H plus ions, protons from the complex ion, and the maximum number of protons removed is the same as the charge on the metal ion. We've given two examples here of bases which are capable of removing protons: the strong base sodium hydroxide, the weak base ammonia. Just have a close look at the state symbol. This particular substance will always be insoluble and produce a precipitate. The M3 plus ion can lose up to 3 protons until it forms a neutral compound. Just one thing on drawing convention, don't use square brackets here because we no longer have an ion. Now we have a summary of various transition elements plus aluminium. We've got their various aqueous ions. Remember, that's when you have the central metal ion surrounded by your water ligand. We've got the various colours they turn. If we start with ion 2, the complex ion of ion 2 forms a green solution. When reacted with sodium hydroxide, we've met this reaction before, it forms a green precipitate. If you add excess sodium hydroxide, you see no further change. How about when we add a weak base to our aqueous ion? This time you'll get a green precipitate. If you add excess ammonia, you get no further change. And if you add sodium carbonate to your aqueous ion, again you get a green precipitate. What about copper 2 now? So here's your aqueous ion, it's a blue solution. We react the aqueous ion with sodium hydroxide, we produce a blue precipitate. The addition of excess sodium hydroxide causes no further change. If you add ammonia again you get a blue precipitate. This time when you add excess ammonia, you lose your precipitate and you end up with a deep blue solution, and if you add sodium carbonate, this time you get a blue-green precipitate. What about iron 3 now? So the iron 3 aqueous ion is a purple solution. If you add sodium hydroxide to iron 3, remember that's a test for that cation, you'll see a brown precipitate. Excess sodium hydroxide causes no change. If you add ammonia to that aqueous ion, you get a brown precipitate. The addition of excess ammonia causes no further change. And then lastly, if you react sodium carbonate with iron 3, you produce brown precipitate and that carbon dioxide gas is released. And now aluminium 3, this time you have a colourless solution as the aqueous ion. Reacting sodium hydroxide with the aqueous ion produces a white precipitate. Remember, when you add excess sodium hydroxide, that precipitate dissolves to form a colourless solution. Ammonia and the aqueous ion produces a white precipitate. And then lastly, the action of sodium carbonate with that aqueous ion produces a white precipitate and carbon dioxide. I know this looks stinky, but you probably already knew from GCSE and IGCSE, the green precipitate here for iron 2, the brown precipitate here for iron 3. If you did AQA GCSE, you'll have learned that aluminium produces a white precipitate with sodium hydroxide. And then at A level, we just need to add what happens with ammonia and sodium carbonate. So that was the summary table we looked at. Now let's look at the various equations, starting with iron 2. So we have our aqueous ion. We're adding that weak base of ammonia. Here's our product, and we're producing the NH4+. As we would expect according to our table, when we add ammonia, we get a green precipitate. So what about copper 2 now? Here's your complex ion. We've changed it up and we're reacting it with our strong base. Here's our product, and we produce water as a byproduct. We already knew that it would turn a blue precipitate here. What about iron 3? Reacting it with our weak base again, producing the ammonium ion, you'll see a brown precipitate here. And then finally our non-transition element, but we're still interested in how it behaves here when reacted with sodium hydroxide. It's going to produce a white precipitate. In these reactions, we can say that the ammonia and the hydroxide ions are acting as bonded Lowry bases, which means that they're acting as hydrogen ion proton acceptors. If we look a little bit more now in depth, particularly here and here, where these are the actual only two reactions that occur with excess sodium hydroxide and excess ammonia. When excess sodium hydroxide is added to aluminium, you find that that white precipitate dissolves, hence why we have an aqueous state symbol here. When excess ammonia is added to copper 2, again, we see that precipitate dissolve, a deep blue solution is formed, and what's actually taken place is that in excess ammonia, ligand substitution occurs after ammonia has stopped acting as a base. That last column then, which dealt with the sodium carbonate solution reactions with aqueous transition metal ions. So we'll take our metal 2+ ions, such as iron 2 and copper 2. Here are example equations of them reacting with the carbonate ion. The iron 2, as anticipated, produces a green precipitate. Copper 2 produces a blue-green precipitate. And now the reactions of metal 3+ ions with carbonate solutions. Iron 3 produces the brown precipitate and that carbon dioxide gas. Aluminium 3 produces a white precipitate and again carbon dioxide gas. And remember that gas will be seen as effervescence, which is in effect fizzing. And just one thing else to point out is that the metal 3+ ions are acidic enough for the carbonate to act as a base and remove protons, but the metal 2+ ions are not acidic enough, and a metal carbonate is formed in a precipitation reaction instead. And so here, because of the 2+ ions, that's why your product here is a carbonate, whereas up here with the 3+ ions, your carbonate here is acting as a base, so you end up with a different product, as we see here. Now, the amphoteric nature of aluminium hydroxide now, we've previously mentioned that it's amphoteric. This means that it can react with both acids and bases. Here's an example of it reacting with acids, hydrochloric acid, a strong acid, to produce this complex ion and chloride ions. This time we have the example of it reacting with a strong base, the hydroxide ion, to produce this complex ion and water. And then last up, before we look at past paper questions, Ligand substitution reactions, when an aqua ion, so that remembers when you have your complex ion surrounded by water, reacts with ammonia, there's no change in coordination number, and that's in large due to the fact that water and ammonia are both uncharged and similarly sized ligands, and therefore the shape remains octahedral. However, if you have your aqueous metal ion reacting with concentrated hydrochloric acid, there's a change in both charge and coordination number, and you go from, in the case of this complex copper surrounded by water ligands, you go from a pale blue solution to a yellow-green solution. Notice a change in coordination number. We go from 6 to 4, and that's because that chloride ion is much larger than the water, and therefore we see a change in shape from octahedral to tetrahedral with a bond angle of 109.5. And then if I haven't given you reason enough to get hold of my guide, this is a great summary, and you know what you do need to learn every single stage, what's happening, the colour changes, the various complex ions, and you'll see why when we look at some past paper questions now. This question is about iron and its ions. Discuss the role of iron as a heterogeneous catalyst in the Haber process. Your answer should include the meaning of the term heterogeneous catalyst, how iron acts as a heterogeneous catalyst, the factors that affect the efficiency and lifetime of the catalyst. It's worth 6 marks. These bullet points are super helpful, don't ignore them. Remember that a heterogeneous catalyst is in a different phase or state from the reactants. Let's define both words. So what is a catalyst? A catalyst speeds up the rate of reaction without being used up. By offering an alternative reaction pathway with lower activation energy. So how does iron act as a heterogeneous catalyst? Well, remember that the hydrogen and nitrogen involved in the Haber process adsorb onto the active sites of the iron. The products, which is the ammonia, deadsorb. And then what factors affect the efficiency and lifetime of the catalyst? Just going to summarize that. Surface area. You want to use powdered iron ideally. The lifetime can be reduced through poisoning. We mentioned that it was the sulfur doing the poisoning in the Haber process. Fe2 plus ions catalyze the reaction between peroxodisulfate 6 ions and iodide ions in aqueous solution according to this reaction. Explain why this reaction is slow before the catalyst is added, and give 2 equations to show how Fe2 plus ions catalyze this reaction. So the first thing to point out here is that the 2 reactants are negatively charged and therefore repel, meaning that the activation energy is high. Let's now write the 2 equations. So equation 1, remember you do have to do an awful lot of learning off by heart in the transition element part of the specification. Give a reason why Zn2 plus ions do not catalyze the reaction in part B. Remember I said that zinc and scandium aren't transition elements. The reason for zinc is because it exists only as the Zn2 plus. It doesn't have variable oxidation states. The figure below shows some reactions of iron ions in aqueous solution. Identify A and state its colour. So because this is a 2 plus ion and we know that the ligands are neutral here for water, that means that's Fe2 plus. So remember, we just did this. If you react Fe2 plus with that sodium carbonate, it's going to produce iron carbonate, and that is a green precipitate. Over here we have Fe3 plus reacting with sodium carbonate. That produces a brown precipitate. The formula is this, and they want the ionic equation for this. Explain why an aqueous solution containing the Fe3 plus ion has a lower pH than that containing the Fe2 plus ion. That's all to do with the size of the ion. So remember, Fe3 plus is smaller than Fe2 plus. I then said that Fe3 plus as a result is more polarizing. So more H plus ions are released, which lowers the pH further. Question 5, which shows the electron configuration of an atom of a transition metal. Remember, we define a transition metal as having a partially filled d orbital. Look down here, that has no electrons in the d orbital. These two are both full, which means that the answer here must be B. Which will not act as a ligand in the formation of a complex ion. So remember, ligands need to be able to donate a lone pair in order to form a dative bond. So it's important you know the structure of these various substances. So obviously the answer here is methane, because it doesn't have a lone pair. The other thing to be aware of, remember, is we've met water and ammonia loads as I was going through the content. They're both monodentate ligands. They're small and uncharged. We met carbon monoxide when we were discussing how it binds preferentially to red blood cells, preventing the transport of oxygen, and therefore is highly toxic. Which shows the correct oxidation state and coordination number of cobalt here. So just count how many ligands are attached. It's 5 plus 1, so 6. And then the oxidation state, we know that this is neutral. So in effect, we're doing 0, which is the charge on the complex ion, minus the ammonia is neutral. That chloride ion is -1. Then we've got 2 chloride ions there. So it's in effect this, which gives us an oxidation state, therefore, of +3. The diagram shows some reactions of aqueous iron ions. Give the formula precipitate J and state its colour. We have Fe3 plus reacting with sodium carbonate. We've already done this. We know that it's going to be a brown precipitate. Here's the formula. And then the equation is the same as before. Give the formula of L and an equation for reaction 2. This is FeCl4 minus another complicated equation. And then we want to suggest a reagent that will take our Fe3 plus to Fe2 plus. From my table, we can see that it's zinc. Give the formula precipitate M and state its colour. So we're reacting this complex ion with ammonia. That's going to produce a green precipitate. Like I said, you simply have to learn these. I'm really sorry. It's super confusing. And then part E, transition metal complexes have different shapes and many show isomerism. Describe the different shapes of complexes and show how they lead to different types of isomerism. Use examples of complexes of cobalt-2 and platinum. You should draw the structures of the examples chosen 6 marks. So in essence, your answer here to get those 6 marks needs to be very similar to this part of my revision guide. Look, we've got the cobalt and the platinum examples here showing the geometric isomerism where the water molecules may be on opposite sides or the same side of that cobalt central metal ion versus our cisplatin and transplatin examples involving platinum, where, if you remember, it's only the cisplatin which has the therapeutic quality of being able to be used in the treatment of cancer. Do make sure to identify the various shapes of these complexes So remember here, these are both octahedral, these are both square planar. And then if you really wanted to max out your answer, you could include optical isomerism shown here, where we subbed in an EN to represent this disgusting NH2, CH2, CH2, NH2 ligand. Do make sure you explain what optical isomerism is. Remember, these are non-superimposable mirror images, in this case in octahedral shaped transition metal ion complexes.